save them for the end. And
Either way, like if I don't know how. I mean, in a perfect world, it would be like if it's pressing for what's on the slide, then ask then. Otherwise, leave it for the end. It's gonna be hard to like make jokes on. So like whatever. I'll go with whatever is fine. Yeah. Yeah. Hey, thanks for coming. Are you doing the interaction? Yeah, it's good. Oh yeah, sure. No, that's good. You know, just to make sure the process or whatever.
Hello, everyone. Welcome to the CS Colloquium. So today we're very excited to have our own Professor Huck Bennett speaking. Huck has been a professor here for a bit over a year, and previously was a professor at Oregon State, has postdocs from Michigan and Northwestern, a PhD from New York University, and most important of all, a master's from CU Boulder in computer science. Glad to have the favorite department here. Huck's research falls in theoretical computer science in computational complexity theory and algorithms in related areas. And today we're excited to have him tell us about the foundations of lattice-based cryptography. Welcome to Huck.
So yeah, thank you very much, Bo, and thanks everyone for taking part of your Thursday afternoon to come. So, naturally on the, okay, good. So the motivating application that I'll talk about today is quantum secure or so-called post-quantum public key cryptography. So let's just remember the setup for public key cryptography. So there are two parties, maybe, you know, an account holder at a bank and then the banker who want to communicate. Maybe they've never met before, right? And they still want to communicate securely so that an eavesdropper can't understand what they're saying to each other. So this might seem wild or actually impossible at first, but actually it turns out that it is possible. And in the late 70s, Ravesh, Shamir, and Edelman showed how to do this and introduced the widely used and famous RSA crypto system. Right? So this message is secure. But then Peter Shor came along in the mid-90s and actually showed that if somebody hypothetically had a quantum computer, then actually it breaks RSA and other similar crypto systems. So what do we do? Well, before going to that, we might ask, like, is this even really a problem, right? Are quantum computers actually going to be built? So there's a lot of evidence that we're making great progress towards building them, including, so there's a Nobel Prize in experimental quantum computing, which half of it went to David Wineland, who was at NIST Boulder at the time of the award. So all of the major tech companies have major efforts going on to build quantum computers. So IBM, Microsoft, they're academic groups who have made major moves towards quantum supremacy, meaning like showing that there are tasks that quantum computers can perform that would take a hopelessly long time for classical computers, and so on and so forth. So it seems like we're making great progress towards building quantum computers. But of course, you know, that's scary because Peter Shor showed that if you have a scalable quantum computer, then it's going to break all of the cryptography that we're currently using on the internet. So, okay, so how do we build post-quantum cryptography? So spoiler, or maybe it's not a spoiler from the title of the talk, using lattices. Okay, so before I tell you what a lattice is, I just want to tell you that actually this is not hypothetical. There's actually a lot of work that's gone into this already. So
You hear this?
things with the eventuality of quantum computers is like if hypothetically somebody records secure communications now encrypted using RSA, they could actually decrypt it 20 years from now when they have a scalable quantum computer. So it's thought that the NSA and lots of other agencies are actually just storing huge amounts of data with the hope that they'll be able to do this. So in other words, we want post-quantum cryptography now, not in 20 years when quantum computers are actually built. And the American National Institute of Standards and Technology has jumped on this. They've done a really good job. So in 2022, they standardized 4 quantum-resistant or post-quantum cryptographic algorithms as winners of its competition. Okay, so here are several. There's a blurb about them, but just the highlighted part in yellow here says that 3 of the 4 algorithms that they selected, they're called Kyber, Dilithium, and Falcon, are based on lattices. So, and in fact, these 2 are kind of the primary 2 that they picked in 2 different categories of secure cryptography. All right, so I haven't told you what a lattice is yet, but lattice-based cryptography has already been standardized for use. Okay, so what's a lattice? So unfortunately, the word lattice is overloaded in math and computer science to mean at least 2 different things. So I see Vishnu smiling. No, Vishnu, it's not a partial order. Here by a lattice, what I mean is a regular grid of points in space. So more formally, if I have some linearly independent basis vectors, b1 up to bn, then I get a lattice by taking all integer linear combinations of those vectors. And I get this regular ordering of points in space. So this is a 2-dimensional lattice. Right, so linear span, I get kind of all of the plane, but if I just take the integer linear span, I just get this kind of discrete grid of points. All right, so why is lattice-based cryptography preferable to number-theoretic cryptography? So number-theoretic cryptography includes RSA and also Diffie-Hellman and other schemes that are broken by Shor's algorithm. So as we said, kind of the top billing goes to their apparent resistance to quantum attacks being post-quantum. They also have a lot else going for them. So they have provable security under worst case hardness assumptions about lattice problems, the so-called worst case to average case reductions. And they also allow for building advanced cryptographic primitives like fully homomorphic encryption, which at a high level lets you perform computations on encrypted data. It's another one of those wild things that sounds like it shouldn't exist, but we have constructions of it using lattices. And also it generally uses simple arithmetic operations. So parts of it, lattice-based cryptosystems, are much more efficient than things like RSA or Diffie-Hellman. You don't have to do modular exponentiation, for example. So just read this as kind of more efficient in certain respects. Good. So, and also lattices are cool. So, the top billing again goes to their applications in lattice-based cryptography, but they're useful in many other contexts. So in optimization, particularly in integer programming, in cryptanalysis, so this is actually breaking cryptosystems rather than building secure cryptosystems, in error correction, and in sphere packing. So for example, the 2022, I think, one of the 2022 Fields medals went to Mariana Vyasovska for showing that a particular lattice packing of spheres was optimal in 8 dimensions. So this is showing the optimal packing in 3 dimensions, which, great. So what I'm going to talk about today is 3 directions that I've worked on recently. So the complexity of lattice problems, connections between lattices and error correcting codes, which, as I'll hopefully convince you, are similar objects, and also a bit about error correcting codes themselves. And then at the end, the problem of deciding whether 2 lattices or codes are essentially the same. I'll say what that means. So, but I just want to share before jumping into that, one of the things that I really enjoy doing is writing about lattices, or just expository writing in general. So I have a few things on that. So if you want to, if something here piques your interest, you can hopefully, or maybe read one of the things I wrote. So when Laszlo Lovász, who's one of the main developers of lattice algorithms, especially the LLL algorithm, won a major award, I wrote, went on a long rant about the algorithm. So this is me trying to break into the tough world of being a lattice influencer. If you want to learn, so this is about lattice algorithms. If you want to learn about lattice complexity, I'd point you to my survey about that. And coming soon, kind of top billing here is that there will be a textbook on lattices, which we have about 300 pages written so far, but it should be done in a few months. So look for that. Right. So let me start by telling you about the complexity of lattice problems. So to do that, I first need to tell you what's a lattice problem. So I'm just going to define one of them, which is the most important problem of lattices. So this is called the shortest vector problem. So the lattice is this mathematical object, but we're computer scientists. We want to compute something about them. So for that, first I need a definition, which is just of the minimum distance of a lattice, which is just the length of a shortest non-zero vector in the lattice. So I'll have a picture in just a second. Okay, and then the shortest vector problem, or SVP, actually define an approximation version of it, is the following. So as input, I get just a representation of the lattice in terms of basis vectors, and I get some distance threshold R. So I also have this approximation factor gamma. Right, so here's my basis. Here I'm not looking at all the points. Remember, this is my input representation of the lattice, but the lattice itself is all integer linear combination of these two vectors. So it's that infinite grid of points. And so the question is, so it's a yes instance of the problem if there's a non-zero point inside the circle, and it's a no instance if all non-zero points lie outside the red circle. So you're promised that one of the two is the case. And this factor gamma is just the ratio between the radii of the two circles. So the radius of the inner circle is R. Okay? And so if we kind of look at the full lattice, or at least the points close to the origin that this basis generates, we see that this is a yes instance because these 2 points are inside of the circle. So in each of those is a shortest vector in the lattice. So they're the x that achieve this parameter here. So I'd love for people to I'll keep going, but this is a big talk, but I'd love for people to interrupt me with questions too. Okay, so kind of the most important parameter for understanding the complexity of lattice problems in SVP is the number of columns in the basis B, or number of vectors, so which is n. So it's called the rank of the lattice. And this problem is really, really beautiful. So you can actually, if you want to study complexity theory, you can see most of complexity theory just by looking at this one problem and kind of tweaking gamma, so which is this approximation factor. And as you do that, I think of this picture as kind of like a slider. So remember, this is gamma, which is the ratio of the radii in the circles in the previous slide. And sort of, if you have gamma as a constant, like 1 or 100 or a million, then the problem with a little asterisk is NP hard. On the other hand, if it's exponentially large, then we can solve it efficiently. And somewhere in the middle here, we actually get secure cryptography, in the sense that if, say, n approximate or n to the 3/2 approximate SVP is hard, in the worst case, there's a worst case problem, pick your favorite, lattice do you think the problem might be hard on, or family of lattices do you think it might be hard on, then we get provably secure cryptography. So this is the worst case to average case reductions part, or security under worst case hardness of lattice problems that I mentioned before. Good. So, but in practice, the way that people think about or analyze the security of lattice-based cryptography is actually just thinking about the fastest algorithms for the exact version of this problem, where gamma is equal to 1. So it's like imagining those blue and red circles are on top of each other. Just you want to know, is there a non-zero vector inside this circle or not? And people make very, very, very precise estimates about the running times of these algorithms, or the fastest that they think these algorithms could possibly run. And the thing is that if they were wrong, we'd actually be in serious trouble. So it's not enough just to show that there's no polynomial time algorithm for the shortest vector problem. In fact, even kind of an exponential algorithm, but like with maybe a smaller base, would actually break all of the real world crypto systems that I mentioned, like the ones standardized by NIST. And if we're even somewhat faster, like 2 to the square root of n, then that would break essentially all real world lattice-based cryptography. So what we want to show is actually that this is impossible, that algorithms for this problem take a long time. Right? So this is one of the funny cases. Cryptography is one of the domains where it's actually good if it takes a long time to solve certain problems. We're building cryptography. The security of cryptography is based on the fact that certain problems are hard. Okay, so to do this, we use the tools of fine-grained complexity. So if you remember, kind of the canonical NP-hard problem is what's called the 3-sat problem. So you have some Boolean formula that looks like this. So for 3-sat, it has this specific form where we have these ors of 3 variables or their negations, and then you take the AND of all of these. And that's a 3-sat formula. So this is the canonical NP-hard problem. So you want to figure out if there's some 0-1 assignment to the variables that makes this evaluate to true. So traditional complexity says that assume that P is not equal to NP, which is equivalent to saying that 3-sat has no polynomial time algorithm. And then the world looks something like this, or at least NP as a class of problems looks something like this. So you get this egg where you've kind of problems at the bottom, which we think of as easy, and problems at the top, NP complete problems that are hard. So P is polynomial time solvable problems, which is kind of easy problems. And then up here, we have NP complete problems. So if you want to show a problem is hard, kind of in the traditional sense, you give a polynomial time reduction from 3-sat to the problem. So you can do that for K-sat or various other problems. But fine-grained complexity says, hey, that's not enough. Actually, that's not conveying a ton of information, just telling me whether a problem has a polynomial time algorithm. We might want much more quantitative information about what the worst case running time of the problem is. And we saw this was motivated in the previous slide. So fine-grained complexity carves up this egg and actually tells you what the precise run, or gives you a precise running time lower bound, or sometimes upper and lower bounds is the case for all of these problems on these problems. So, but to do this, you make stronger assumptions. So you make assumptions of the form. So there's what's called the exponential time hypothesis, which says that 3-sat not only has no polynomial time algorithm, but actually requires exponential time. And the strong version of that says that K-sat, where you have not just 3 of these variables in each group, in each clause, but actually K of them, takes 2 to the n time, which is saying that like brute force is the best you can do. You can always solve this 2 to the n time just by enumerating all 0-1 assignments to x1 up to xn. So in assuming this, the strong version of this, the egg of NP looks like this. So to note, like showing these results is not just a matter of making some stronger assumption, which may or may not be true. It involves showing very efficient reductions. A reduction is really an algorithm itself. So very efficient algorithms mapping instances of one problem to the other. So, but of course, there's a question, what about lattice problems? So in the previous slide, we said that there's strong motivation for trying to prove strong computational lower bounds on lattice problems, trying to show that they live near the top of this egg here. Right? We want to say that lattice problems, like the shortest vector problem, take a long time to solve. And that would give us confidence in the security of lattice-based cryptography. Okay, and so not surprisingly, this has been a focus of my work, is studying the fine-grained complexity of lattice problems. So I won't tell you the details of all of these papers, but I'll just drop some pretty pictures and citations, and I'm happy to talk about this later. So for the shortest vector problem and a related problem called bounded distance decoding, we have a slew of results, and actually in work with co-authors starting in 2017 and follow-up work in 2021, we kind of introduced the study of the fine-grained complexity of lattice problems. So in each of these papers, in different ways, shows computational lower bounds of the form that I showed in the previous slide. That a problem like SVP takes, like, say, exponential time in some sense, but there are lots of different twists and caveats to this, which are covered by these different papers. There's also still a lot to be done. Okay, but just to highlight one thing, so you can think about, we're kind of in this world where, why are polynomial time algorithms kind of the magic thing? Like that's what you learn maybe in undergrad complexity or whatever when you learn about P and NP, but really is polynomial time so special? So you can think about, what happens if you allow kind of algorithms, protocols, and reductions for lattice problems, or just in general, to run in, say, like 1.01 to the n time. So still kind of like small exponential time instead of polynomial time. And then, so if you remember, this is kind of the map of complexity we saw in the previous slide. And in work with co-authors, we kind of showed that in the exponential time world, actually these middle boxes look like this. And so without getting into too many details, you can kind of pattern match here and see that these quantities are about a square root of n factor smaller than the corresponding quantities in the box above here. And what that means, like in practice, is that under an arguably weaker assumption, we get provably secure cryptography. So that's a good thing, right? Like, just we have more confidence in the security of lattice-based cryptography. Okay. No questions so far. Okay, cool. So next thing, if like shifting gears a little bit. So I'm going to talk about error correcting codes and their connection to lattices. So we'll start with just like one slide, which could be like the beginning of a coding theory 101 class. And I'll connect back to lattices in just a second. But here's the famous diagram in Claude Shannon's master's thesis, which is like, people are like, this is the most important master's thesis of all time, which I think is like 60,000 citations. So, I mean, I think it has it's definitely in the running. Okay, so the main use of error correcting codes is actually robust communication. So we talked about lattices so far. We said they have a bunch of applications, but we mostly talked about them as being useful for designing secure cryptography. In other words, enabling secure communication. So error correcting codes have similarly various applications, but they're best known for their use in robust communication. So let's just think about this at a high level. So say that we want to encode a k-bit message in a redundant way. So how could we do that? Let's say that k is equal to 4 as an example. Well, maybe the first thing you think of is you just repeat each coordinate of your message 3 times. Right, so 0, 1, 0, 0 gets mapped to this thing, which is 12 bits long. And then you can tolerate any of these bits any single bit getting flipped and still recover the original message. So why? Say that one of these ones got flipped to a 0. Then still, if while being sent to your friend, still at the end, you can take a majority vote among each group of 3 and still recover the original message. Okay. But you might ask, okay, actually 12 bits is a lot, or like blowing up by a factor, the message length by a factor of 3 is kind of a lot. I wonder if we can do better, meaning like somehow still tolerate one arbitrary error, but do so using kind of adding fewer bits to the original message. And the answer is yes. So here's what's called the Hamming 7.4 code. It has its own Wikipedia page. So the idea there is that to encode a message, what you do is you take this matrix G. It doesn't matter so much what it is, just you can think about its properties. So you multiply G times your message. So think of your message as a vector of length 4. And you'll map M to whatever, like to some code word here. And it turns out that this code word, so you can see, is only 7 bits long. And it turns out that it actually also, this code protects against one arbitrary error. So you can do better by, here we got down from 12 bits to 7 bits with the same redundancy guarantee or robustness guarantee. So, but you can think about what you might want. What should a good error correcting code do for you? Well, you want a code where n, which is like kind of the total length of what you're sending, is as small as possible, and the number of errors tolerated is as large as possible. And so here we're talking about one error, but in general, you can see if you repeated like 5 times, then you could tolerate any 2 errors, for example, and so on and so forth. Okay, so on this slide, I'm going to do 2 things. The first thing that's maybe the most important for connecting to the rest of the talk is just to emphasize kind of the definition of what's a linear error correcting code and observe how similar it looks to the definition of a lattice. So this has the form. This definition says a code you get from a matrix G. So here F2 you can think of as it's the set 0, 1. So it's just bits and you perform arithmetic mod 2. So just like multiplication works the way you think it does. And then addition, if you add 1 and 1, you get 0 instead of 2. We're a computer scientist, so that's no particular problem. So addition is XOR. Right? Okay, and so what's the code generated by G, which is a matrix that has k columns and n rows? Well, it's just all linear combinations of these columns. So you can observe that actually, if you replaced F2 with the integers, then in each of these 2 cases, then this would just be the definition of a lattice instead of an error correcting code. So in a precise sense, codes are like the finite field analog of whatever. Just think of this as, with bits, the bit analog of lattices. And so similarly, just like with lattices, an important parameter for codes is what's called the minimum distance of the code, which is just the minimum distance between any 2 distinct code words. So here, this norm 0 thing just means, so I have my first code word, I have my second code word. They're both vectors of length n. I take their difference and I look at how many non-zero coordinates they are. Equivalently, it's just the number of coordinates that x and y differ in. Right? Like if both of them have zeros or ones in a coordinate, it doesn't count towards this sum, but if one has a 0 and one has a 1, then it counts towards that sum. So this is just the number of coordinates that x and y differ in, is what this part is. Okay. And it turns out that this parameter is super important for determining how good an error correcting code is. So basically, an error correcting code with minimum distance d can correct up to off by 1s and floors about d over 2 adversarial errors. So for example, in the previous, or say in the first code that we saw, the repetition code where we just repeat everything 3 times, that code had minimum distance 3, and so it can correct 1 adversarial error. So what coding theorists do for a living is try to understand the trade-off between 3 parameters. So you have your message length k you have as input, and you want somehow the code word length to be as small as possible and the minimum distance to be as large as possible. But another way of saying that is just like you start with n and then you simultaneously want k and the message length and d, the minimum distance, to be as large as possible. And it turns out that when coding theorists think about to what extent this is even possible to do, and they've come up with a whole bunch of bounds, which are shown, 5 of them are shown here. Actually, the green one is different from the other 4, to show to what extent this is possible. So this shows like basically the 4 bounds other than the green one show that like there's only so good your error correcting codes can be. Like if you want to be able to correct against like 17 errors, then there's some, like you're going to need to kind of add at least a certain number of bits to your initial message in order to have it be sufficiently robust. All right. So, but one impact or just one implication of these bounds is that they tell you that in a given code, there must exist pairs of code words that are close to each other. But they don't tell you how hard it is to find them. It just says, hey, pairs of code words that are close to each other exist, but Like, how do you actually find them? So in recent work, we actually studied this problem. We're like, okay, we look at all these bounds. We can tell you like what the complexity of actually finding pairs of code words is. And we do something similar, like they're analogous bounds or for lattices, and we also study the problem in that context. Okay, so complexity of lattices and codes. So again, these two objects are intricately related. So just to mention a couple of other things I've worked on with this. So one is so again, like what's the first thing you might want to know about hardness of a problem? If you've taken kind of even undergrad complexity, you're like, okay, if I want a problem to be hard, I should show that it's NP hard, right? So it turns out that the shortest vector problem, it's sort of known to be NP hard, but there's like a weird caveat on it that it's NP hard, but only in some randomized sense. So it's a major question that people care about. Like, you try to delete the word randomized from this and just say it's NP hard. Like, it's kind of the first thing you'd want to know about the shortest vector problem, but embarrassingly, we can't even show that about this most important problem related to lattices. So, but in work from 2023, we showed like kind of the simplest randomized, still randomized proof for hardness proof for SVP, and also like gave a plausible approach for de-randomizing it. And to do this, we use lattices built from the world's coolest codes, which are called Reed-Solomon codes. And in another work from 2023, we kind of almost fully resolved the so-called parameterized complexity of the shortest vector problem and kind of the analogous problem on codes, which is called the minimum distance problem. So just trying to figure out what the minimum distance of a code input code is. And so this kind of actually this previous paper that's listed here solved what was kind of one of the biggest open questions in parameterized complexity, and then we in turn kind of answered the main open questions from that paper. Okay, so another connection, this will be related to another connection between lattices and codes, but we're back to having some nice pictures. So just this slide will just be about something just related to lattices. So you can ask kind of this question where suppose you kind of have one sphere, maybe in one dimension, maybe in 2 dimensions, 3 dimensions, 4 dimensions, whatever. You can ask, so one unit sphere, how many other unit spheres can you pack around it so that they all touch the central sphere? So in 1 dimension, it's 2. It's shown in this picture. In 2 dimensions, the answer is 6. In 3 dimensions, it's 12. And I think it's known for 4 dimensions, I think it's 24. For 5, it's an open question. Nobody knows the answer. So, but even though if you, like me, can hardly visualize 2 dimensions, let alone any more dimensions, like this sounds hard, but fortunately we have tools like from linear algebra and that let us reason about these things without actually visualizing. Okay, so the Kissing number of a lattice, so say that you center each of these spheres at a point in your lattice, that's one of the things you can do. That's one way that you can arrange points around other points. So if you have like a lattice arrangement like this, the Kissing number of a lattice is just equal to its number of shortest non-zero lattice vectors. So in 2018, Agarwal and Steven Savitowicz showed that if there's a family of lattices with very large Kissing number, exponentially large Kissing number, then actually just the existence of that geometric gadget, it's just the existence of a lattice, that's enough to prove strong complexity results about the shortest vector problem and would let us conclude cool things about the security of lattice-based cryptography and rule out certain attacks, right? So this is cool. It's like if some math thing, is true, then the existence of some geometric object implies like strong complexity results. And then in follow-up work in 2022, we refined their technique and showed some other strong fine-grained complexity results, assuming the existence of these gadgets. And then it seemed like our timing was good in 2019 and 2021. Actually, a pair of papers that were published in good math journals showed or claimed to show that lattices with exponential kissing number exist. So this is cool. It seemed like that means that like now our results aren't conditional anymore. We had cool, strong hardness results about the complexity of SVP. And the idea behind this construction was to build lattices from suitable error correcting codes. So maybe just because I didn't explain the details of this, but you saw that the two objects, the two definitions are similar enough that maybe it's not surprising that there are ways of building good lattices from good codes. But it turned out that actually most constructions of lattices from codes, including the ones used in this paper, actually kind of don't preserve kissing number. And so it turns out that it seems like the approaches in these papers actually don't work. And so these 3 papers were retracted after following up on our work. So this remains like a nice open question for people to think about. Okay. So I was talking about kind of connections between lattices and error correcting codes, but I also want to mention one other line of work that I've been really excited about, which is actually using error correcting codes, which again are most famous for allowing for robust communication, to help actually design fast algorithms. So it might seem funny, but we actually want to design fast algorithms using ideas from coding theory. So the problem that I've looked at here for doing this is the matrix multiplication problem. So what's the matrix multiplication problem? You get 2 n by n matrices A and B, and you want to compute their product. So this is like one of the most fundamental computational tasks. Like kind of basically, I think most of science and machine learning and everything, applied math, like at the end of the day, you're like, oh, this is hard. I'm going to linearize whatever my problem is, and then, whatever, do some linear algebraic task on it, like solve a linear system, which is you can do using matrix multiplication. So naively, matrix multiplication takes n cubed time, but actually a long line of work has worked really, really hard to get faster and faster algorithms. And the current record, which is from 2025, is like about n to the 2.37. You can ask, say that we're promised something about A and B. Like specifically, the thing that we considered is what if the product AB is actually sparse? You could also ask about whether the input matrices A and B are themselves sparse. Like in that case, can we do something better? Can we get a faster algorithm for this super important problem? And in work with Karthik Gajulapalli, who visited me this summer, he's a visiting student, and Evelyn Wharton, who's my PhD student, and Sasha Golovnev, we showed in a pair of papers is that the answer is yes. And actually to do this, we use techniques from coding theory. So let me just give like a scenario for this, like, why might this be a problem that we're interested in? So here's the setup. So actually, it turns out that matrix product correction is equivalent to output sparse matrix multiplication. So here are 2 faculty members, CU computer science professors. And sort of the setup where Alessandro on the left here, who studies robotics, so he has some problem with his robots, and he decides that he needs to solve a linear system to solve his robot problem. And so he heard that Maria has an awesome new GPU cluster. So like she can probably do matrix multiplication way faster than he can. So Alessandro sends his matrices to Maria. She computes the product, but she sends the answer back on a noisy channel. So maybe some of the entries just a couple of the entries get flipped. So we have like n squared entries overall, but maybe like a few of them get corrupted on the way back to Alessandro. So he wants to be able to recover the actual answer from the input matrices and the approximately correct output matrix. And using our algorithm, he would have a way of doing that efficiently, more efficiently than was known. Okay. So what's the upshot? Just error correcting codes are not only useful for robust communication, although that's one important application, but they're actually useful. They're connected to lattices, right? And let us build nice lattices. And also actually error correcting codes or techniques from coding theory are actually somewhat surprisingly really useful for designing fast algorithms as well. So kind of the last kind of thing that I want to talk about. So just have a few slides about this. So the problem of deciding whether two lattices or error correcting codes are in some sense essentially the same. So what do I mean by that? So to describe this, I'll tell you about like kind of a special case of it, which is like how we can get some sort of simple lattice-based cryptography from rotations of CN. And so I'll tell you about a crypto system from a paper of ours from a couple of years ago. So in Atul and Pora, these two authors were actually undergrads at the time that we did this work. Cool. So basically what this is doing, like what we're going to do is we're going to kind of work with what are essentially the simplest lattices, which are rotations of the integer lattice. So the integer lattice just looks like this thing on the left. It's just take all integer points in n-dimensional space. You get this square, or say in 3 dimensions, cubic looking grid. So here, you can imagine this is like 0, 0, 1, 0, 0, 1, 1, 1, and so forth. But you can imagine extending that to higher dimensions. And then you can imagine doing something where you actually, okay, now you grab the entire lattice and you just rotate it by some amount. And you get a lattice that looks like this on the left. Or sorry, on the right. So here's our crypto system, and I'll just explain how we can use it for encrypting a single bit B. Right? So, okay, in general, you might say that's not very many bits. I want to encrypt more bits. But you can do various things like including repeat this several times. So just like as a side comment for students who don't know who these two pictures are of, like go look it up. Okay. Right. So anyway, Alicia wants to send 1 bit encrypted bit to Bob. So just a 0 or 1. And how is she going to do this? So first what happens is Bob, who's on the receiving end here. So he has this rotation and he decides on 2 different representations of the lattice. So one of the things that makes lattice problems hard is there are actually many ways of representing them. There are, in general, infinitely many different bases of the same lattice. So, and Bob is going to take a good basis of the lattice as his private key and give Alicia a bad basis as her public key. So what makes a basis good? Its vectors are short and nearly or perfectly pairwise orthogonal, right? So here it's as good as we can get. We have like these form a 90-degree angle, and actually these are shortest vectors in the lattice. Okay. And so how does Alicia encrypt a bit? Yeah, Ken.
So you have your lattice as it's been rotated. Every point has integer coordinates.
That's right.
Rotation. Most points have floating point.
Yes, so that, which is a major mess, like if you're trying to implement this, right? Like, because that could matter a lot. So actually, one way of handling it, I'm hiding it. This is, but you can actually use what are called quadratic forms, and then everything will still be integral. So like, you'll actually work with something which is the matrix B. Like if you have a basis B, you actually look at B transpose times B instead of, and then somehow you can get rid of worrying about floating point for the most part. But that's a really good point. So like if you rotate, like it's going to be a mess, like even just trying to represent this lattice, because you might need really, really high precision not to make mistakes in various ways when you're trying to do arithmetic with it. Your question or yeah.
So from a cryptanalysis perspective, if I know that the private key is going to be like orthogonal and shortest vectors, that's still some information I can try to attack, right?
You can, but like so we have this is speculative, and it's very possible that this ends up being insecure, but we do have evidence that should be hard. right? Like, so there's like, I think it's Kirchhoff's principle. The idea of designing crypto systems is that like, everyone should be aware of the design of the crypto system. The only thing that's secret is maybe the keys, right? And so like here, everyone knows that the good basis is going to look like this, but the thought is that that's not enough to actually let an attacker do much. So as it turns out, like finding this basis is more or less equivalent to solving the shortest vector problem in this lattice too. So which we think even for rotations of Zn might be hard, even though these seem like the simplest lattices ever. Awesome questions. Anything else? Yeah.
So this rotation, is that
No, that's private. And that's important that it's private too. Yeah. So like just going back, like here, you know, if you just like the lattice is unrotated, everyone knows you're starting with Zn. So if like you just literally have Zn, then it's easy for anyone to find like a perfect kind of great basis. And so if you know what the rotation was, then you can just kind of first rotate it back and then find it yourself. So it's important that the rotation is secret. Good. Okay. So we have this secret rotation of Zn. And again, you know, in 2 dimensions, you're like, give me a break. I can just fiddle around a little bit and tug it back. But like in more dimensions, we like 100 or 1,000 dimensions, we think this is hard. Yeah.
Have like a public key with one bad basis. Is there concern about like, is this something where you only have one good basis and for one private key and one public key, or is there concern that you could reconstruct the lattice if you had multiple public keys and had more, kind of get more information about that lattice from multiple public keys?
Yeah, that's a very good question. But like if you kind of like you can imagine if you construct these randomly, even by sampling, then actually having a lot of public keys wouldn't help. Like there's a way you can make that formal where like anyone can take this public key and turn it, or this good or bad basis and turn it into other bad bases fairly easily. It's the hard part is turning it into a good basis. But also like say there are a bunch of people who want to communicate with Bob, they can all use the same public basis. So like you don't need one public basis per person. Like it's enough just to have everyone sees this. The whole world sees this basis. Yeah.
Could you just repeat the questions for the folks on?
Oh, let's see. So the most recent question was like, does sort of publishing or having multiple bad bases like distributed or shown to the world make the crypto system less secure? And remember, Ken's question was about like, isn't there a horrible floating point error if you try to rotate Zn? And oh yeah, another is like, is the rotation actually, does the rotation need to be secret, or is it fine if that's public? I think that was maybe all of them. I don't know. Sorry. Yeah, you're quite.
Yeah, are they pairs or like I have a good basis, I can generate n number of bad bases from it and use
Yeah.
like for public keys.
So yeah, but again, like you only need one, but hypothetically, actually you can generating bad bases is easy. Like you can generate a bad basis either if you have a good basis, or even if you're starting with a bad basis, you can easily generate other bad bases. So, and like, yeah, you can show like whatever, like a polynomial times sampleable distribution of bases that as long as you have any representation in the lattice, any basis, you can sample from that efficiently. So like that's somehow the right distribution to sample this from. Okay. So let's see how, whatever we have, we have this nice setup. So how are we going to actually use this for Alicia to send Bob one secret bit? So the idea is that the encryption of B, so inc of B, is going to be a pointed space, not a lattice point, just some pointed space, right? So with an n-dimensional lattice, like it's kind of embedded in n-dimensional space. And so Alicia is going to do one of two things, depending on whether she wants to encrypt a 0 or 1. If she wants to encrypt a 0, she samples a point close to the lattice. And if she wants to sample a 1, she samples a point far from the lattice. So you might see there's some this is imprecise. I'm not saying exactly how you can do this, but this is intuitively the idea. There are certain distributions of points that are either close or far from the lattice and have nice properties. And the idea with decryption is that Bob, with his good basis, so again, what's Bob's goal? So he wants to know whether Alicia was trying to send him a 0 or 1. He just wants to be able to tell whether we're in the scenario where we're close to the lattice or far from the lattice. Right, so as long he sees the ciphertext, which would be one of these, either like the red point or the blue point. But using his good basis, he can kind of just, he looks in, he does kind of has this change of basis because of the rotation, but he's actually able to just kind of round a coordinate at a time and actually efficiently compute the exact distance from whatever the point is to the lattice. And from that, he can tell whether it's close or far from the lattice. Right? Whereas the thought is that if somebody like an eavesdropper only sees the bad basis, then they would not be able to do this efficiently. So just to be clear, this crypto system is not what was standardized by NIST, but they use ideas which are in some ways similar to this, where like you kind of have this situation where you're either close or far from the lattice, and that's how you encrypt it. Yeah, Ken.
Is the bad basis is still used in some way to say, go in this direction to find my close points from my far point?
So yeah, so Alicia it turns out that Alicia can generate these like either a close or a far point, even just with like, even though she only has somehow a bad representation of the lattice. So like this question. Oh yeah, so the question was like yeah, how's the public key used to sample, I guess, these points, or like, is that a problem for Alicia if she wants to do it? So I can tell you the far case, yeah. So the far case, what you do is like, basically what you want to think of intuitively is you just sample a random point in space. That's impossible because there's no uniform distribution on the plane. But what you can do is take just like kind of one unit cell, so like a square like this, and sample a random point inside of that. What you do for the close one is you actually just pick a lattice point, say 0, and you sample points from a Gaussian with narrow variance around the point, and then shift it so that it lands inside like the unit cell. So but you can do that even with the bad basis and still achieve kind of distributions that are either close or far from the lattice. Yeah.
Sorry.
No, that's great.
Are the parameters for that easily computable from the bad basis, or would you have to still construct
the parameters just depend on n, which is the dimension of the lattice, basically. Also, like there's a trade-off where somehow the point is like if this is a focus of a lot of work on lattices, but kind of if you pick your points in the close case from like a very narrow distribution, then there's less chance you'll get confused that your point came from the far distribution. But on the other hand, it's somehow like less secure, like because you're kind of, if you're close enough, like really, really, really close to the lattice point, then there are efficient algorithms for even if you just have a bad basis to recover your distance or what the closest point is. But on the other hand, yeah, so you want, if you have a higher variance Gaussian, then you kind of look more similar to the far distribution, but you might sometimes get confused about which, or even Bob might get confused about which of these distributions the point came from. So there's this tension between security and correctness. Yeah.
Could you repeat the question for the chat?
Oh, yeah, sorry. So it was basically about, yeah. So for this close distribution, the question is like, so I said that you sample kind of points from a Gaussian more or less around one point and then kind of shift it so it lands in a unit cell. So the question is like, I think something like, yeah, like what does that distribution look like? And does it depend on the bad basis? And I was saying the key idea, it basically just depends on n, which is the dimension of the lattice. So. Okay. So just to summarize, so there's a generalization of this problem, which is called the lattice isomorphism problem. So here's again kind of just a special case where, so here we have like Zn or Z2, which is with like kind of the nicest basis imaginable. And here's some rotation of Z2 kind of with a bad basis. So it's simultaneously a rotation and has this bad basis, right? And so the lattice isomorphism problem in general is just to decide you're given two lattices as input, say specified by bases, and you just want to decide if one is a rotation together. So recently, it's been a very hot area of research to kind of build cryptography off of the assumption that this problem is hard. And so the crypto system I just showed you from our paper kind of used this problem, but just in the special case where one of the two lattices is just an integer lattice. So, but you can study this as a computational problem in and of itself, and it's very interesting. So, but in work from 2016, we actually studied a generalization of this problem where you don't just ask whether one lattice is a rotation of the other one, but you actually kind of want to know if kind of how similar the two lattices are in some sense. Like maybe you could get from one lattice to the other, not just by a rotation, but by a rotation and maybe a little bit of stretching. Is lattice, like that's the distortion. So, but it's a measure of how similar two lattices are. And then one other problem I've been interested in recently is the analogous problem on error correcting codes, which is called code equivalence. So code equivalence, like just an easy way of thinking about it is say that you have an error correcting code, and well, really you'd have a very similar error correcting code if you just kind of permuted all of the coordinates of each of your code words. That really wouldn't change the structure of the code. And so they're twist code equivalence, but basically that's just what code equivalence asks. You get two codes as input, and you just want to know if you can get from one to the other just by permuting the coordinates. So in work with my student John from 2025, we kind of related the code equivalence problem to the lattice isomorphism problem. We also had some other results, but for the purposes of this talk, that was like the tie-in. So, but studied the complexity of this problem in general. And then in work, actually with from an REU led by Jean-François Biassa, we had this paper where we have the fastest known algorithms for the code equivalence problem. They're like randomized in quantum algorithms. And this was really cool because three of these authors, these three, were actually undergrads who are participating in the REU. But this is super cool because it was like this is like a paper that I'm quite pleased with, and it came out of work at an REU. Like in an REU, you're like, okay, it's just nice to expose students to things a bit, but you're not necessarily thinking that you'll get anything particular out of it. Right. Okay, and yeah, that's it.
So yeah, we had a bunch of great questions during. Let's take a couple more minutes for more questions, and also for Zoom, put questions in the chat.
Yeah.
So at the beginning you talked a little bit about advantages of lattice and lattice systems. Can you comment a little bit on some disadvantages?
Yeah, like key sizes are larger and certain operations are slower. But like, yeah, that's the answer. But oh, sorry, yes, sir. It's really yeah, that's hard to remember. Yeah, so the question is like, so we said I was bragging about how great lattice-based cryptography is. The question is, are there disadvantages, or what are the disadvantages of it? So yeah, so the answer is like, yeah, so kind of from a complexity standpoint, like more space and time necessary for certain aspects of the cryptography are necessary. But there have been major improvements in that, and there are charts where we're comparable to certain number theoretic cryptography, or even faster in some cases too. Yeah, and certain things are easily parallelizable too. I think people are actually designing hardware now to like do some of the operations that are used in these things. So you need operations like the fast Fourier transform to make lattice-based cryptography super efficient. So whatever, but yeah. So that might impact things really actually in practice too. So not just asymptotically. Yeah, Jed.
What is the key size? And I guess that's the statement
Yeah.
of two things, because you have dimensionality and the like resolution.
So-
essentially.
Yeah, well, there's a lot of stuff. So the first and like answer, first order, highest order bit is I don't know. The second one after that is, so of the crypto systems that I mentioned, there's both a key exchange mechanism, which is like public key cryptography, and then a digital signature scheme. And they have actually considerably different parameters used in them. And then also for each of them, there are 3 levels of security. There wasn't just one crypto system that NIST standardized. They're like very similar, but you can tweak the parameters. Like at a high level, you make n bigger if you want more security. And so then the key size is like the parameters are quite different in those 2 cases. But like, yeah, even for like getting the order of magnitude right, I don't want to mess it up. So, but like I can point you shortly to the document where it's written. So, yeah.
There's a question from the chat. Nicholas is asking if it's easy to generate close far points from a bad basis. Why is it hard to decode close far from a bad basis?
Yeah, that's a good point. So it's sort of like in one direction. You can like generate the point, but it's hard to, I don't know, at least hard for somebody else to figure out where it came from. Yeah, I don't know if I have a good punchy answer to that, but that's the idea.
Easy to break an egg.
Yeah, easy to break. Yeah, something like hard to put it back. Yeah, so but it's we think it's like a one directional thing that it's easy. Yeah.
How do you argue about the proofs of the lattice-based crypto systems?
Like why it's secure or
yeah, what are the sort of techniques?
What was the question?
yeah, or sorry, yeah. So I see. So so why should we imagine this is secure? So I see Josh has a question too, but yeah. So I mean, again, this is not just one more time. This is not what was standardized by NIST. This is our thing, but it shares certain similarities. So actually, one thing that so I wish I had a slightly different picture here, but you'll have to just use your imagination to say one of these like squares is kind of filled in, right? You can imagine that if you have kind of fill that square in just uniformly, like all the same shade, meaning like sample a random point from that square, uniformly random point, then actually you'll get a similar distribution to what you would get if you took kind of a wide enough Gaussian, actually not close, but like a super wide Gaussian, and then shifted the point in there. So that's actually like kind of one of the key things that like observations that makes lattice-based cryptography I don't know how we argue about the security of lattice-based cryptography. So somehow in some precise sense, like Gaussians and the uniform distribution kind of look similar, or we think they do to an adversary if you have like the right parameter in your Gaussian. Like again, it only makes sense if like you sample a Gaussian point and then you shift it into this. So like there'll be contributions like from eventually kind of you imagine I don't have the right picture to show this, but that's the idea.
Josh.
Oh yeah, Josh.
Oh yeah, sure. Can you hear me?
We can't hear.
Hello, hello.
Well, he knows where to find you.
Yeah, he knows where to find me. Yeah.
Yeah, fine. All right. Well, thanks everyone, and thanks to Huck for the.
Yeah, thank you very much, Ian, for coming. I wasn't sure if I'll send